Okay, I'm Will Martin. I'm going to be talking today about my graduate research project. What we have over here is just a prototype mock-up of a quadcopter, and these are where the four propellers would be. One of the problems that we have in working with quadcopters in the lab is stability. They tend to drift, they tend to have little pitches and yaws that you don't want, and it's very hard to control just with the controller. So our thinking is that if we have a camera on the ground here looking up at it, and we take a series of pictures, one where these lasers are on, another where the lasers are off, then we can take a difference image and extract these 4 points from the image. About a decade ago, someone else here at the Iris lab, Chandra Tan, developed a thesis about a 4-point pose estimation algorithm, where if you know the geometry of this thing, and you get 4 pixel locations based on where these points of light are, then you can tell the pose of this quadrangular object in 3D space. So that's kind of a top-level overview. Eventually we're hoping to have a feedback control system on the brains of the quadcopter itself, where it takes this information about its pose in 3D space and uses it to stabilize or do path planning for the quadcopter. So the system I have is using Matlab to control the camera and process all the images. Right now I'm going to run the system. We'll do 30 iterations. I'm going to press go here, and it takes a while to establish the communication link with the Arduino that controls the laser pulses, but here you can see a little GUI where we have the 2 images, one with the lights on, one with the lights off. This is a false color difference image. You can see that these 4 points of light are showing up nice and bright. Here's a graph that shows a model of the quadcopter in 3D space. You can see that if I twist the quadcopter, then its position in 3D space on the screen twists as well. Similarly, if I increase the pitch of the quadcopter, the pitch increases in 3D space. And then on this screen I have a bunch of information about the pose being spit out to a terminal. We know our east-west deviation, how much right to left we're deviating from the center point of the camera. We also know altitude, pitch, roll, yaw, everything that describes this object in 3-dimensional space. We also have a way to view similar information on an Android device. So on this Android device, I'm going to go ahead and pull up an app that I wrote. I call it Quadrangle Tracker. So,
Glare.
Okay. So we have server settings. This communicates via TCP/IP protocol using socket programming from the computer to the Android device. So here I can set the host IP address of the computer and the port. I already have those correctly set for the program. So here in Matlab I'm going to add an optional argument to my function, just a number 1 telling me that I'm going to be connected to the Android. And we're going to start the program over again. So after it goes through its initiation routine here on the screen, waiting for a connection, I've got a button on my app called Start Tracking. I'll press that button. It says that we're successfully connected, and now all of the information that we had available to us on the computer we now have available to us on the Android device. For instance, this gauge right here, pitch, that tells you how much the quadcopter is pitching. So if I change the pitch over here, then on the app now you can see that my pitch is 25 degrees. I set the quadcopter back down flat, and now the pitch is back to roughly 0. I also have the ability to switch to a 3D view. This is a little bit slower because it's actually just taking a screenshot of that 3D graph on the computer screen and sending it over the internet to the Android device. But now the same graph that I had access to on the computer screen and I have access to on the Android. I can switch back to my standard view, and then I can tell the computer that I want to stop tracking. On the computer screen over here you see that it read a queue, connection ended by Android. And then it gives, on the Android I can browse my run data. So here I can see my all of the pose kinetics for the quadcopter for every data set that we had in that run. I can also browse previous data. So here's just date stamps of all the other times I've run the program. If it's taking up too much room on my device, I can delete that previous data, get rid of that, assuming that we've already offloaded it to the computer. So that pretty much sums up where I am right now. The next phase of the research is that right now this runs at about 1.6 seconds per frame. Clearly that's too slow, but most of that has to do with all the overhead that Matlab has associated with it. So we're porting this algorithm over to Microsoft Visual Studio C++ so that we can have executable that runs much faster.